Okay, yeah. So thank you everyone for attending this Informs QSR webinar. I'm Chao Wang, and this webinar is co-organized with Dr. Mawson from New Jersey Institute of Technology. And today we are very glad and honored to have Dr. Yao Xie from Georgia Tech. So as Dr. Yao Xie is preparing the slides, let me just give you a very brief intro for Dr. Xie. So Dr. Yao Xie is Coca-Cola Foundation Chair and Professor at Georgia Institute of Technology in the H. Milton Stewart School of Industrial and Systems Engineering, and the Associate Director of the Machine Learning Center. She received her PhD in electronic engineering with minor in mathematics from Stanford University in 2012 and was a research scientist at Duke University. Her research lies in the intersection of statistics, machine learning, and optimization in providing theoretical routines and developing computationally efficient and statistically powerful methods for problems motivated by real-world applications. She received an NSF Career Award in 2017, the Informs Wagner Prize finalist in 2021, the Informs Gaver Early Career Award for Excellence in Operations Research in 2022, and the CWS Woodruff Award in 2024. She's currently Associate Editor for IEEE TIT, JASA, the American Statistician, OR, Annals of Applied Statistics, Sequential Analysis, IJDS, and Area Chair of NeurIPS, ICML, and ICLR, and also a Senior Program Committee of AAAI. Yeah, let's welcome Dr. Xie. Yeah. And Dr. Xie, please.
Okay, so can you guys hear me fine?
Yes.
Okay, great. So first of all, thank you so much, Dr. Wang and Dr. Shen, for organizing the seminar, the webinar, and having the chance for me to talk here. It's my great pleasure and honor to talk about our recent line of work along so-called guided flow generative model. So without much further ado, let's get started. Okay, so I'm pretty sure we all have experience with Gen AI nowadays, right? There's Gen AI in every aspect of our life. I think from ever since 2023, ChatGPT has been very popular. We can ask questions, even feed homework questions, and it's going to give an answer to the question, right? So this is, I guess, professor's nightmare that I'm trying to, hopefully not having students doing this, but they can use this to help them understanding knowledge. And also for image video generation, and this is one picture that my son tried himself the other day, and it turned his picture with his friend into Simpson style. And so besides these image, text, and video generation examples, it has also been used in many scientific domains such as protein structure, and I have one project on this, a NASA project with my collaborator at Georgia Tech. And another project I think might be interesting and related is to generate some synthetic moon surface images. And this is a project developed while my student was doing intern with NASA. And the goal is to generate some moon surface that is realistic and they can use to test the moon cars they're developing. And so from our perspective, right, so generative AI is very powerful, but I think essentially it can also be understood if it take a step back that it is a way to represent high-dimensional distribution. Of course, it's very different from our usual understanding of representing distribution or density, but essentially what it does is we have these training data such as many pictures of the birds and dogs, and they are sampled from some very complicated high-dimensional distribution that we don't know. And so essentially we have this generative model that can learn from these training data, remember the pattern, and when we can generate new samples, new pictures of dog and birds and frogs that look realistic and similar to the data we have feed in. So it is an implicit representation because we still don't know what does the distribution look like, but we can draw sample from it. And it is very capable of handling high-dimensional distribution, which is a appealing feature, I think, very intriguing and making us thinking about how to use it for our applications with high-dimensional data. And so in statistics and machine learning, what are some typical representing distributions? For example, the traditional parametric model is we pick a certain function class of models such as Gaussian, which is parameterized by the mean and variance. And learning such model means given data, we try to estimate the parameter values. And so sometimes this gives a lot of nice statistical theory and guarantees consistency, but it can also be limited in that it makes strong modeling assumptions. And so to get away from such a strong smoothing modeling assumption, because sometimes it can be a mismatch from data, there's also non-parametric models such as kernel-based method, smoothing splines. And so as you can see, for example, for the same data, if you fit a non-parametric model, you can discover the data has two modes instead of being just one mode that is imposed by the Gaussian assumption. And so it is useful to discover, let the data speak for itself. However, the traditional non-parametric models also face a challenge such that it has a curse of dimensionality in high-dimensional data. And so given the generative model's capability to generate samples look realistic to the training data, we're hoping that this can be used as an implicit way to represent high-dimensional distribution. And it is scalable, right, clearly to high dimensionality of the data. And so, but we also hope that we can get a handle of the theory behind generative model to make it give the similar kind of results we hope to get from the classical approach. To relate back to the audience here, I think in particular in our society and community, we're interested in studying reliability and robustness of the algorithms. And I'll give two examples why, what do we care about, I think. So for example, one example is worst case generation, right? So in manufacturing systems, we have data from the sensors, from video cameras to monitor the production line and robotic arms and so on. And so we're hoping to detect anomalies as quickly as possible from the data. And so we have some data for training, but there could be worse scenarios we haven't yet observed from data. And so the question is, can we generate some synthetic defective scenarios from data? In energy system, we also are interested in, for example, in find out how the power grids is going to behave under extreme weathers, how bad it can be, how much outages it will be in the entire power grid systems. And so I have a project with Argonne National Lab in particular trying to study this problem. And in healthcare applications, for example, nowadays there's a lot of interest and motivation of using AI predictive algorithms in monitoring patients, for example, in ICU, and predict the risk of the patients developing sepsis, which is a very dangerous disease that can happen to a patient. And so with the deployment of such sepsis prediction algorithm, and we want to ensure these algorithms can still perform well, even in out of distribution means the setting, which means that the patient is experiencing some situation that we haven't seen in the training data. So the question there is how poorly the algorithm can be, even in the worst case. And so if you look at these motivations, and this is clearly different from the current generative model delivers, because the current generative model is you train the model using some training data, and it is very good at imitate what has been observed from the training data. But we're asking how much worse a situation can be from what we have seen. So the fundamental question here is how can we model what is not being observed yet, and under that, how bad our algorithm can be, and making a prediction under this worst case, but yet not yet observed situations. It's like a test on the algorithm, a stress test of the algorithms. And so another application, or I think critical pillar in this regard, is uncertainty quantification. And so, for example, in predictive maintenance, we're interested in estimating remaining residual lifetimes, but we also want to do this with confidence interval, right? So to quantify, for each, for example, prediction and what is the range of possible residual time. And so I give an example. This is one of my projects with Luna technology. And there we have lots of sensors placed on different parts of the airplane. And so these sensors provide real-time measurements and readings to monitor the coating health status. And so, for example, if there's any rust spot is forming, we want to be able to detect and predict as quickly as possible and schedule the next maintenance, repainting, recoating to prevent any further damage. And so with lots of sensors at the same time, we're facing a high dimensional challenge. And to predict and what is the remaining lifetime or schedule a future painting time, we hopefully want to be able to generate some scenarios. And another example is, for example, in image reconstruction, we have some noisy and imperfect observations and try to recover the image. And so can we quantify the uncertainty in our estimate? And similar situation can also happen in digital twin, for example, calibrate the model and assess reliability under parameter uncertainty. And so this is another example, as you can see, well, here we want to measure our confidence in our prediction using a noisy and incomplete data. And so statistically, a lot of times this can be framed in the Bayesian language, calculating the posterior of a prior given our noisy and incomplete observations. And we're also asking the question, like, if we have a generative model we already trained for our prior using the data, before observing any new data, can we compute the posterior to update the generative model from some observation? And so these two pillar questions, the first one is worst case scenario generation. The second one is uncertainty quantification, or UQ. Provide the motivation for us to consider beyond generating models, just imitating the training data, but provide a worst case sampling and posterior sampling. And I will present the guided flow as a unified framework to approach this. Okay, so before we start talking about the guided generative model, let's first review what are some typical generative models nowadays. So one of the earliest versions of this is generative adverbal zero networks, the GAN models, which was quite popular, I think, since 2014. And there's also variational autoencoder. And more recently, I think the popular models are the score-based diffusion models and normalizing flow models. Here I listed some of the developments. And sometimes these models have different names, such as flow matching, rectified flow, consistent model, and mean flow in the most recent I think, iterations of these kind of algorithms. The nature of this generative model, largely speaking, is it is a large neural network with certain design and architecture that can transform a noise sample into a data sample. For example, on this plot, on the left-hand side, you take one sample out of the white Gaussian noise, right? So it is very easy to sample from white Gaussian noise, right? In high dimensional, this is one of the easiest distributions to sample from. And so essentially, this neural network can remember the pattern of the data and convert the noise sample into, for example, a picture of the cats. Right? So all the information is contained in this neural network. And these different choices of generative model, GAN and VAE, for example, is basically designed this big neural network in one, big shot, like one step, and try to develop the whole big neural network. So people later on find out it is very difficult to achieve one, transformation, like try to find this transformation F all together using one big neural network. And you're going to see all kinds of issues with mode collapsing and, failing to generate good images when you go away from training data. So, and because of that, I think these later diffusion models and normalizing flow type of generative models is changing this problem from training one big neural network into training a sequence of blocks of smaller neural networks. So I would say the analogy would be, if it's hard to make things happen in one shot, we can make small iterations to gradually guide the noise towards the data. And that is precisely, I think, the kind of illustration happening in these two types of diffusion versus flow generative models, which is popular nowadays. The top one is this picture I took from Dr. Song's blog. And so he explained the so-called score matching. And so the idea is, you can see it has two processes. And so the so-called forward process is trying to learn a transformation to gradually convert image into noise domain. And then if this pattern can be somehow learned and remembered, and then we can use the reverse time stochastic differential equation. And then you can take a fresh sample in the noise domain and run this process in reverse time and be able to recover, convert this noise sample into a sample of the image. So behind this, essentially, there is a principle that you can actually play back time and convert the image into the noise, but also from the noise to the image. And so this is because of the principle of reverse time SDE. And so there's another large categories of such kind of gradual transformation turns noise into a data sample. That is called a flow-based model. And in particular, it is based on ordinary differential equation instead of stochastic differential equation. So on the top of the SDE score matching, the idea is you have to gradually add noise. And then in the reverse time, you also have to add a noise to generate sample. And so the flow-based approach is you don't add noise, actually. You try to find a deterministic way to convert the image, a sample from the data domain, and using a sequence of deterministic mapping to convert it into the noise domain. And if you find these transformations are invertible, you can also take a fresh sample in the noise domain and convert it back to a sample in the data domain. And so, the fundamental differences, like I said, the flow-based model is based on ODE, or ordinary differential equation. And so it is deterministic without adding additional noise. So usually it is more efficient in generating samples. And you can imagine, right, the trajectories of converting samples is straight because you don't add any noise in the process. Versus the score matching based diffusion type of generative model, we add noise in the process. And so this is still going to mathematically able to do the job, but on average, this relies on, you have to average out the additional noise we have added. So that's the SDE counterpart. And mathematically, you can prove actually these two approaches are equivalent. If you set the parameter for one type of model to be related to the parameter of the other type of model. But implementation-wise, the ODE approach or flow-based generative model have seen some competitive advantage in terms of efficiency and more reliability. Okay, so with this being said, let me start to explain what is guided generative model and how do we build this on top of the flow-based generative model. So today's talk is largely going to be focused on the flow-based deterministic ODE type of generative models. And so largely speaking, this kind of generative model is we take an existing generative model and we're going to convert that using another guidance procedure. And this guidance is going to convert this existing generative model towards something we like, such as the worst case sampling or posterior sampling. And what is this guidance? This guidance can be coming out of risk objective of our choice, if we want to achieve worst case sampling, or this can be likelihoods, which is given a particular observation, how is it related to the underlying ground truth that we don't observe? So this can be used for posterior guided sampling. And so I think the guided flow generative model under these two pillars really build a bridge between the existing data-driven imitation type of generative model towards our goal of achieving sampling from the unseen and go beyond generating the training data. And so what is the core idea in building this guided flow generative model is we find that there's interesting theoretical connection between guidance flow with continuous map between probability distributions. And so here's an illustration. And so as you know, this is basically the idea of three stages, what happens. So on the right hand side, right, there is this flow from multivariate Gaussian towards data, right? So the flow is two direction. You can go from the data to the noise, and because this model is invertible, then you can also take a sample in the noise domain and map it back to the data, right? So this right hand side is basically the original generative model that can imitate the data pattern itself. But the guidance is basically saying that suppose we already have this, right? You take this and we want to be able to learn a way to convert this into do something else, right? Which is not just mimicking the data, but sample worst case distribution or posterior. So that is the objective, to drive or guide this data distribution towards some Q. This Q is our worst case distribution or posterior. So how do we approach this mathematically? And we're going to rely on this concept of transport map. And so this transport map is basically essentially it's a mapping from RD to RD if D is the dimension of your of the data, right? So essentially it tells us if I give you a data point, how do I move this from one position to another position? Okay, so it's literally like you're transporting some masses around in the D-dimensional space. And so this transport map is applied on the data point itself. But as you can imagine, the data are sampled from some distribution. So if we change the data, it will also change the underlying distribution. Okay, and so that's what we define as this transport map T sharp. And on the right-hand corner, so I wish I could have a pointer, but somehow, let me just try it one more time. Maybe this will be better. And then you can see my mouse. Okay, great. So just one sec. Let me just do it this way. Okay, great. So yeah, you can see this is a transport map T, and this also causes a so-called push forward of the distribution P to so-called Q. So as you can imagine, essentially, if I can move the masses around, I can convert the distribution from this to this. And in fact, you can find out the optimal transport map can also induce the Wasserstein-2, for example, distribution. Wasserstein-2 is a metric to measure the distance between the two distributions. And so this is because of the so-called Bernoulli theorem. It is held under the assumption that P and Q both have continuous densities. But largely speaking, you can see what it says is if I can find a way to move the data X to some other place, Tx, and then the amount of movement, I measure this as T minus Tx, X minus Tx squared. So square the distances and taking expectation, take the average over the distribution of my data from the P. And then the transport map that will minimize this expected square loss is going to reduce the Wasserstein-2 measure between the two distribution T and Q. Okay, so this is one of the two definitions of Wasserstein distance, but it is a fundamental definition. Okay, so we have this transport map. We're going to use this a lot and look at how do we drive the distribution from one to another. Essentially, you can think about this as a way to model our guidance. And so how do we, make this abstract T, implementable in practice is we're going to borrow this idea from continuous time flow generative model and look at how things are moved around in a continuous time fashion. And this T is actually a fictitious time. So essentially you can think about if I can somehow have a continuous way of moving my data from time 0 to time 1, and at any given time little t, and my data position, right? This is a very basic physics, right? So if you look at the position of my data at time t, the first order derivative is going to be described by the velocity evaluated at the position and also at time t. So how do we visualize or understand this is you can imagine you have the space, you have lots of data in here, and then for each position, and you have a certain direction and also magnitude of moving this. And this can change for different position and different time. And so if I can, continuously pushing the particles around, this will also change the underlying distribution of these data. For example, convert that from this to this. Okay, and so if I do this over a time horizon from time 0 to time 1, and so essentially the transport map can be defined by integrate this velocity field over the time horizon 0 to 1. Okay, and so like we said, if you change the particles, the data in the data domain using velocity field, and this is related to the T transport map, and you can actually change the underlying distribution, and actually you can describe how the distribution is changing using this so-called continuity or loop-value equation. And so think about if I can design a certain way, right, choose a certain velocity field, and that means I choose a certain T, then I can, potentially drive my distribution from some P to a Q. And actually the way this moves in the space of distributions is it's going to move on this manifold of distributions. And why it is a manifold? Because the distributions have to be on negative, and they also needs to integrate to one. So they're not just arbitrary function, right? So they have some constraint. That's why it is actually a manifold. Okay, so this way of describing the way to change distribution by moving the data actually can be implemented in the flow type of generative model approach. If we discretize the time by discrete time intervals, essentially we can say for each time step, how much we have moved the data is going to be from the starting position, and you integrate over some velocity field over this time interval, and this is the forward direction. And then since we're interested in the invertible mappings, because as you can see, we want to be able to convert into something but also go back. And then the inverse of these maps is easy to find by just integrate back in time, right? So if I just, I think this is a fundamental reason I want to look at parameterizing the velocity instead of the t transport maps, because if you parameterize the velocity field, then you can find the inverse of these mappings easily. If I parameterize the t by neural network, then I cannot be guaranteed this is invertible. Inverting a neural network is not trivial. But if I parameterize the velocity field by neural network, then I can make it invertible. And so after time discretization, and my overall transport map is just the composition of a sequence of these. And apology for the typo. Okay, so with this in hand, now we can tackle our problem. And so the first version is of the basic flow generative model. And in this case, you can think about my goal is to drive my data distribution towards Gaussian and also go back, right? So and remember, I have many small mappings in discrete time step, and each one of them is basically a neural network parameterizing the velocity field, and this is actually called the rest block. And I have to mention that this idea is actually coming out of the classical neural ODE, I think popular neural ODE paper, which was in 2018. And so, so we can imagine essentially we're trying to learn a sequence of these maps. Each of them is parameterized by some neural network through the velocity field. And then if we want to drive the data distribution into noise, such as a distribution of the rows into a noise like this, right? Within each of the block, you have some kind of rest block, and the architectures can be simple, feed forward, or depending on your data, it can be convolution neural network. If your image, you have images, or it can be graph neural network if you have graph data. And then my training objective, how do I tune these sequence of neural network block is I can choose my learning objective to make sure I gradually convert my distribution towards Gaussian. So I can minimize, for example, the KL distribution, KL divergence between the distribution that I'm converting this towards to Gaussian. Okay, so this is training objective. And so in fact, there's also efficient training scheme based on a sequence of iterations. You can train one rest block at a time. And so this is the so-called JKO scheme. And so you could say that I can solve a sequence of optimization problems. In each iteration, I froze all the rest block I have trained so far. I just tune the next rest block. And I can achieve this by minimizing the KL of the output of this towards a multivariate Gaussian and with some regularizer. And so this actually has good performance. We are also be able to prove its convergence guarantee. Okay, so this is, the generative part, which is imitating data. You want to find a way to move the data distribution towards Gaussian. And so what's new here is, as you can imagine, we're not just interested in finding a mapping from the multivariate Gaussian towards data, but also towards some other Q. This represents the worst case distribution, or uncertainty quantification such as the posterior. So how do we do that? So you can imagine we're going to go from here to P and also to some other Q. And so I'm going to first talk about how do we formulate the worst case sampling and to find this Q. And that is going to achieved by introducing a guidance that is associated with our choice of the risk objective. So this is the worst case flow-based generation. And so the formulation is inspired by this very popular Wasserstein distributionally robust optimization, which is, I think, nowadays quite popular in OR, community, in machine learning. And so essentially the idea is to say that you're trying to find the solution to this minimax optimization problem to make your algorithm robust. And so inside this formulation, first, the objective is to say, suppose I choose a certain risk function, such as in classification, this risk function is the logistic loss. It is evaluated at the data, and the data is following a distribution Q. Okay, what is Q? Q is a distribution within my uncertainty set. So this P is my so-called reference measure. And you can imagine this P is the distribution we have from data, right? This P, you can say constructed based on my training data. This is what I know, what I observe. But I'm going to consider not just the P, but the distribution Q that are close to the reference measure P within a ball. And this ball is defined by the Wasserstein 2, as we introduced earlier, right? This is measuring the distance between Q and P. So we're saying that let's consider the distribution Q that are within radius R, Wasserstein 2 distance from the reference measure. And let's consider all the, such distribution and find the one that actually will make my risk the worst, right? So this Q actually is a worst case distribution that maximizes my loss. And then the robust algorithm is basically choosing the theta, is represented by theta, that will be the best choice against the worst case distribution in this reference measure. Okay, so this minimax formulation has been studied a lot, in particular in establishing, how to find theta. But there actually is a computational challenge of how to find this Q, because finding the Q involves if you want to consider all the possible Q, including continuous distribution. And this is going to be an infinite dimensional problem because Q is a continuous function. So computationally, it is difficult if we don't introduce additional structure. So the idea here is we're going to represent this Q with our generative model. Okay, so I will show this actually falls into our framework, and you can represent it this way. And so consider this inner maximization problem. First, we can write this Q essentially belong to the uncertainty set is a constraints. Using Lagrangian technique, we can write this constraint as part of the objective. This lambda is the Lagrangian multiplier that can be related to the radius R. And then we consider this associated minimization problem. And so, in fact, now we plug in the definition of the Wasserstein 2, and then you can find essentially in the end, I can reformulate my problem finding Q as the problem finding this transport map that will minimize this objective. Okay, and this transport map now, remember, I can parameterize with my neural ODE, and I can parameterize using this velocity field, discrete S time, and this corresponds to the sequence of neural networks I can use to represent that. So this is the main idea that we used in this paper to find the worst case sampling. Okay, so now let's look at one example. What does this give us? And so this is an example of the adverbal zero learning. So the risk function is the logistic loss. And so as you can see on the left-hand side, right? So this is, if you take the original generative model that generates a picture of the dog, it is gradually converted towards a sample that will minimize the loss. Maximize the loss, right? Make your classifier mostly confused. And so you can see the picture of the dog is converted into a picture of the frog, and the horse become a bird, and so on. Okay, so this is an example of what this gives us. And I also want to say that this can also be used in a related problem, which is differential privacy. And so here, instead of finding the perturbation of the generative model to give the worst case distribution, here you want to find a distribution that you can introduce noise to your data to hide the privacy. Okay, and so this distribution of adding noise, what distribution of this noise needs to be, it doesn't need to be Gaussian, doesn't need to be Laplace. These are the two common used distribution in the past. And we show that if you learn this distribution using this framework, and then this actually will hide your privacy better. Okay. And so I mentioned the key element, which is how do we find this inner maximization? And actually, we can also solve this together with the outer minimization. And this will give us some kind of iterative scheme, right? You can do minimize factor theta and maximize this factor Q and solve a sequence of such problem. In the end, this is going to give us both the worst case sampling and also the robust algorithm parameterized by theta. And in these papers, we showed the convergence of this kind of mini max optimization problem. And so how do I show that? And there's an intrinsic connection of this kind of problem with Wasserstein, gradient descending Wasserstein space, also called the Wasserstein gradient flow. And so essentially what happens, as you can imagine, our optimization problem involves this Q, which is the distribution, like we mentioned, this lives on the manifold, right? So it's infinite dimensional. And so we can build an analogy actually between the optimization in the distribution space and with Wasserstein 2 distance, with the usual kind of optimization problem in the vector space if you choose the Euclidean distance. And so actually there are interesting mathematical analogy between the two approaches. And leveraging that, actually we can adapt the proof techniques in proving convergence of minimax algorithm to our problem involving a vector and a distribution. And so in particular, the concept of convexity and weak convexity, and these can be generalized to distributions with Wasserstein 2 distance. And so it's called the long generalized geodesic. And so this is giving a picture. I don't expect you to fully read everything in real time. I just want to explain the high level idea, right? So because we're able to build the analogy between the vector space and the distribution space, and we're able to prove the convergence of this. Okay, so that's one pillar that I just highlighted. How do we do worst case generative model? And the next pillar I want to highlight is how do we do posterior based samples, and in particular posterior flow based sampling. Okay, so I think this is another important use case for our community because we're interested in quantifying the uncertainty. And so let me illustrate here what, so essentially the application scenario could be following. So suppose we observe a noisy and incomplete, very corrupted image. And so in this extreme case, you can see this image, we only observe 10% of the pixels with noise. So you can barely see there's something inside. It's actually a bed, okay? And so now we're trying to recover this image. Okay, this is the ground truth. We don't know. This is the actual image. This is our observation because it's very difficult to figure out what is the original image. And so this problem has been studied in the past, for example, in the context of matrix completion, right? So how to figure out the missing entries. And so there are many good point estimators, basically trying to estimate a X hat, right? So from this incomplete and noisy Y. And so here we're interested in saying, can we also quantify the uncertainty in our estimates? And so what does it mean? So for example, if we say this is our Y, and we have some kind of generative model for all the bad, okay, all the beds. And so before seeing the Y, we just have some generative prior. This is the prior we have on all kinds of pictures of the beds. And now we have seen the Y. We can compute the posterior. Okay, the posterior is to say that what is this going to be this underlying picture of the bed? What does it look like? Once we have seen this Y look like this. And so Bayes' rule says this is basically going to proportional to the prior. And now this prior is going to be represented by the generative model and times this likelihood function. This likelihood function is a forward model, essentially, sometimes called. It basically says if my underlying picture is X, what is my observation Y? And this involves some kind of observational models. And so if we could figure out this Q, and in particular be able to sample from this Q, sample from the posterior, and this is going to be very useful. For example, if we draw 5 samples out of this Q, and these are the 5 posterior samples. And you can see, because the image is very noisy, we tried our best to recover the image, but there's, many places we're not certain. Across these 5 recovered images or generated posterior samples. And you sometimes observe, this window place in particular, it look like this. Sometimes you have curtains, sometimes you have something on the wall. But in a bad region, we're pretty consistent that we know there must be a bed in this region. So if you look at across all the samples, and essentially this green box is a region we have low uncertainty. We're pretty consistent, we're pretty confident that this is a bad. But in this window part, somehow, we don't have enough information. And so you can see a lot of varieties on this region. So that's indicating a high uncertainty region. So this is a made up example, but I hope this convey the message that this can potentially be used to quantify the uncertainty in high-dimensional image, high-dimensional applications. And this is mainly in this paper, the CVPR 2025. Another related paper is this one, ICML 2025. And so how do we sample from the posterior? Okay, so again, taking this picture of guidance, right? So suppose we already have a generative model. This generative model tells us how do we convert a Gaussian into data distribution. But now we're interested in getting a Q, which is our posterior distribution. So we need to learn this process as well. Okay, this phi is given to us. You can use any generative model you like. It could be, in particular, this phi, I'm going to consider it is a flow-based type of generative model. This can be JKF flow, can be consistency model, it can be rectified flow, can be your probabilistic flow, any deterministic mapping, okay? And this is given to us. And so this basically is a deterministic mapping from a sample in the Gaussian towards sample in the data. So I'm using the subscript 0 and 1 to indicating 0 is in the data domain and 1 is in the noise domain. This is our fictitious time. Okay, and so if I have this generative model, essentially this provides an approximation to the data distribution. And now we're trying to find out the posterior, right? The true posterior of observing the y is the probability of the data, at time 0. Okay, this is our data domain. Condition on y, and this is proportional to the likelihood times the data distribution. And of course, we don't know this, and we can replace this with our generative model. This is our generative prior. And so this is giving us this approximate P tilde. And it's, same likelihood, but this part is given by the generative model. I'm using the phi push forward of the Gaussian. And so actually, interestingly, right, this can be done, in one line of proof, you can show that because of this blue box, because you map the data using phi, right, from the noise to the data. And you can also show that this happens to the posterior, approximate posterior as well, that the approximate posterior in the noise domain is pushed forward using the same phi to the posterior in the data domain. Okay, this is the key observation here that enables us to develop an efficient algorithm to sample the posterior. And so this is basically a simple change of variable. And so what this tells us is basically that we can show then the posterior we're interested in, this is the approximate posterior in the data domain, is proportional to the likelihood. Okay, but this likelihood is basically saying that suppose I take a sample in the noise domain, and then I can propagate through my mapping phi, and this gave us some kind of, guess of the image, right? And that matches to my observation. At the same time, you can compute this gamma, right? But this is very easy. This is just the Gaussian likelihood. Okay, so this basically gives us this kind of efficient posterior sampling by the Langevin dynamic with guidance. Okay, so let me highlight this part. And so what does this mean? So the algorithm is basically saying that now we're trying to find a posterior sample, but we don't have to do this in a data domain at all. We can do this in a noise domain. So you can find a trajectory of the samples, the sequence of the samples in the noise domain. But you have this phi. This phi helps us to go from the noise domain to always to the data domain and try to match the y in terms of the observational model. Okay, and so this is basically the algorithm here. You can see it's very, very simple. And we build the algorithm based on the so-called Langevin dynamic. So it basically says that if I could generate sample according to this, stochastic differential equation, but important part is you can see this is the additional so-called guidance. And this guidance is the gradient of the log likelihood. This is my likelihood function. And then I think there's probably a log. Apology for the typo. There's a log. So the gradient of the log likelihood function evaluated as the mapped forward sample of the noise, right? And so if I don't have this, it's just the original basically sampling in the generative model, okay, for the diffusion model. But when we introduce this additional guidance, and it is introduced by this phi. This phi is some additional, generative model provided to us. This provided guidance that actually give us the posterior sampling. So that's the main idea. Okay, so this actually gave us really good performance. We reported complete evaluation in that CVPR paper. It is very computationally efficient. In particular, we compared this with a state-of-art popular diffusion posterior sampling. And the difference is here, we rely on this flow-based deterministic mapping phi to achieve the samples without having to leave the noise domain ever. So this is just generating the sequence of the noise, and each one of them is trying to convert it into the posterior samples. And so the alternative approach actually had to, for each initialization, run the whole noise trajectory. So computational-wise, it is very expensive. And so this basically evaluation shows that this flow-based posterior sampling is very, very efficient in achieving posterior samples. And it also has good posterior mean estimate. So remember, we want to recover the image, and this is some example. And so we tried, for example, when the observation is missing data and when you have some blurring and the Gaussian blurring and so on. And so as you can see, compared to the ground truth, right, this is our approach. And this is some other approaches. You can see the image recovery part is done pretty nicely. And so this is one example, right? This can be applied for, you can see it's quite general. As long as I can specify the observation likelihood, you can plug into this framework. And this is just illustrate, suppose my observation is through this kind of additive Gaussian noise model. And this A is my observational model. For example, you have missing data. This is observing a subset of the pixels. And if you have a blurring image, this is basically a linear operator, and so on. Okay, and so in that case, the log likelihood function look like the following. Okay, so this A is given to us. And so then the Langevin dynamic is basically the following. So if I want to do this posterior flow-based sampling, I just need to take the derivative of this respect to x1. And this can be done fairly easily, okay, numerically. And so, yeah. And finally, I also want to mention that we also have the theoretical guarantee for this approach. And so basically it says if we can guarantee the generative model for the prior of the data to be sufficiently good. Okay, so it doesn't need to be precise, but if we can bound the quality of the generative model to be some epsilon, and this can also induce the quality of the posterior sampling to be a similar precision up to constant. Okay, so this is what we can prove. Okay, so in the remaining, I guess, 5 minutes, I will just talk about, some extensions or possible other related problems that you can imagine. The main idea is we want to take this beyond just Gaussian as our target. And for example, we could also achieve guidance using data-driven samples for the Q. For example, you could say I can provide some samples of the Q. I want to find a way to drive my P distribution towards the Q. And so this could be in the application of transfer learning. For example, I have some pictures of the bed and I have some picture of the shoes. And so can I find a way to convert pictures of the bag into picture of the shoes, for example. You can do, domain adaptation, and we call this flow-based Schrodinger bridge because Schrodinger bridge is trying to bridge to distribution P and Q that are completely general, but we're doing this in a deterministic flow fashion. And so somehow as a byproduct, we can also use this to evaluate the likelihood ratios or density ratios, in particular for very difficult distributions. For example, this side is P, the other side is Q. You can see one is 2 moon. That means your data sits on these 2 positions. And then these other white regions are low density regions. You don't have much observation. And then the Q is going to be this checkerboard. It has a very different support. So if I just directly divide P by Q, and then in the region, you don't have a lot of common data points, the estimation is very poor. And so now once we have built a bridge between the 2 distributions, we can build a telescopic sequence to help us to gradually estimate density ratios such that in between, right, these two observations, then I have much more data in common, then I can estimate each of the terms much more accurately. And this is my example. For example, my X is this, this blue, the other one is the Q, Y following this. You can see I have very different support. And so if I know the distribution, in population precisely, and this is the ground truth of the density ratio. And then this is using our telescopic density ratio estimation, enabled by being able to bridge the two distribution. And you can see this is matching the ground truth likelihood ratio pretty nicely. If you just use a naive KDE, this is the result. You can see it is very stripy and not a good quality. Okay, so I mentioned this in particular because I think density ratio estimation is a basis for anomaly detection. And so I think this can be used for building an algorithm for that. And very quickly mention that it's not just a static problem, but this can also be used for dynamic problems. For example, we can use this in a conditional generation framework, and where, for example, you want to train a robotic arm to learn how to pick this object, right? So you have some demo, but you hope to learn a control policy, in a reinforcement learning setting to mimic this action, right? So, and actually we're able to adopt this flow-based approach to represent the policies in reinforcement learning and achieve good performance. Okay, I guess that's the end. So basically what I just mentioned is, we want to go beyond just mimic the data or imitation of the training data and generate samples that look similar to the training data, but use it to generate worst case samples or posterior samples. And interestingly, I mean, on the surface, these two problems may not be related, but somehow I think we find they both can be modeled as guidance. And by solving, a guidance of the existing generative model using a flow. And then this can give us, one is done by solving the minimax optimization formulation of master state space. The other one is done by guide a pre-trained generative prior by the likelihood function. So they're both some kind of guidance. But I think I can imagine there can be more situations where we want to adapt or change an existing generative model towards something else. And so I think there could be interesting connection of this towards, say, few-shot learning or in-context learning, which is a similar kind of, you want to adapt an existing pre-trained generative model towards something else that fits your goal. So that's my talk, and acknowledging the support by NSF. And this is done, work done with many collaborators, including Xiuyan Cheng at Duke and my former students, and also others. And so here's a list of references. If you're interested, I'll be happy to share them, and I'll be happy to take any questions. Thank you.
Yeah, thank you, Dr. Xie, for this very fascinating technique and very promising applications. Yeah,
thank you.
Yeah, so any questions from the audience? Please feel free to unmute yourself. Yeah, maybe I can just give a quick kickoff. Yeah, so I see you use the Gaussian, in the technique in essentially when you generate the represent noise part, noisy domain. Is there any reason like you choose Gaussian besides say it's very easy to sample? Is there any like say related property that must be used Gaussian during the, especially say the convergence analysis?
Okay, that's a very good question. So first of all, like you have commented, Gaussian is one of the most commonly used, sample space because it's easy to right in the high dimensional space. Mm-hmm. And I think my own feeling is also because it is also infinite support, right? So although it is centered at some mean, right, with some spread controlled by your covariance matrix or variance. But in principle, you can get any sample in the domain, right? And so this is different from if you have a uniform distribution, and that's sitting inside a compact domain. And that means there are certain regions you will never see any samples. So if that happens, then if you somehow want to convert samples that should come outside of this box, that you cannot do it, right? Because uniform distribution sit inside the box. And so I think that is, practical reasons. But I think behind that, theoretical reason in our proof for the conversions and so on relies on one assumption, which is actually quite general. I mean, it's not restrictive or anything, is in order to use the transport map representation, we need the P and the Q to both have continuous density. So it means that hopefully they have, they're absolutely continuous with each other. Means they cannot have any, they both have some density. They cannot have atoms, put it this way, okay? So Gaussian satisfies this. But it is not the only distribution that satisfies this, but it satisfies this. So there's nothing like in the proof that we must tailor to Gaussian, but the minimum requirement is P and Q both need to have densities.
Sure. Yeah, thanks.
Okay. That's
Actually, a quick follow-up, if I may. So I'm not sure about the location of the mean in the Gaussian. Is that important? Say, suppose we allow mixture Gaussian.
Yes.
Will that make things more complicated, or
That's a great question, actually. I can say I had some slides before, but I think I removed them later. You can do Gaussian mixture. In fact, in this paper, the invertible neural network graph predictions, and we actually use the Gaussian mixture. We sample from Gaussian mixture instead of Gaussian. And you raised a very good question from your good intuition, is that if we have Gaussian mixture, and we have to ensure these Gaussian components are sufficiently separate, means that if you look at the distance between each of the Gaussian components relative to their variance, I think about that some kind of SNR, right? So this needs to be sufficiently large in order for us to have good performance. We show this both in experiment and also in theory. And so we need the SNR to be greater than certain lower bounds in order to have consistent result.
I see. Yeah, thank you. Thank you very much.
Yeah, thank you. Thank you, Shao. Yeah, and also to follow up on the Gaussian mixture, I think there are also recent results on diffusion models where you have a target as Gaussian mixture instead of Gaussian, and such as by the group of authors in Wharton at UPenn, at Yuting Wei, and co-authors and so on. They look at sample on Gaussian mixtures and diffusion models in particular. So we'll consider flow type of model, which is different. The proof techniques, but I think a lot of things are in common between two type of approaches.
Yeah. Thanks.
Thank you.
Any other questions from the audience, please?
I do have one question. Thank you, Dr. Xie, for the brilliant presentation.
Thank you.
Yeah, so I noticed that when you use generative AI to generate the priors, and the model itself, it would introduce uncertainty, right? And then your data distribution would also have uncertainty. So the posterior distribution that you have, the uncertainty quantified by the posterior distribution. Is there a way to kind of disentangle the uncertainty from the model itself and also the uncertainty from the data, and then because this way we can know how good the data is, and then and also whether there's model bias from the prior generation. I don't know if that's a good question, but
yeah, that's a great question. I think I hear your question. So let me rephrase it. So what I heard is, you have the X, right? X0. And then suppose you have many pictures of the bat, right? So there are variations in that. So there's intrinsic uncertainty. And then on top of that, if I fix an X, you have the observation, and you introduce noise, blurry, missing pixels, and then this noise or uncertainty introduced by observation. There are two sources of uncertainties, right?
Yes.
And then in the posterior, actually, this is due to the two sources. Question: can you entangle them? So I think no, the uncertainty we quantified is due to both of them. Okay, so the fundamental reason is because this is from the base formula. The base formula basically depends both on the prior and also this likelihood. So this is the type of overall uncertainty. So if you want to achieve something like you described, you want to separate the two. I don't know. I think it's a sort of like a different question. It sounds more like to me like you want some kind of conditional generative model saying condition on the observation, right? And so that means I fix my observation, right? I fix my underlying X somehow. I just want to quantify, for example, the uncertainty in the Y. That is the uncertainty due to your observation. And
Yes.
then that's like a conditional generative model, I think. It sounds to me that's the direction of to go, but it's not, this type of generative model, posterior sampling, indeed.
I see. Thank you so much.
Yeah, no problem. Thank you for the question.
Okay, so yeah, I think we run out of time, and let's just thank Dr. Xie again. Yeah, and thank you for all the audience for the attendance. Yeah.
Thank you, everyone, and thank you in particular, Chao and Bo. It's great meeting you here, and look forward to seeing you in person next time.
Sure, maybe in Informs. Yeah.
Yeah, see you at
Yeah.
Informs. Thank you. Bye.
Bye.
Bye bye.